Hello and welcome. Today we're going to delve into a fascinating phenomenon. Why is the sky blue? This question has puzzled many of us since childhood, and today we're going to unravel its mystery. The answer lies in the interplay of sunlight and our Earth's atmosphere. It's a tale of light scattering, atmospheric particles, and varying wavelengths of light. So, ready to uncover the secrets of the sky's color? Let's start with the basics. Sunlight. To understand why the sky is blue, first understand that sunlight isn't just yellow or white light. Sunlight, in fact, is a mixed bag of many colors. This radiant array of hues, known as the visible spectrum, stretches from deep reds to vibrant violets with every color of the rainbow in between. Each color in the spectrum has a different wavelength. Red light waves are longer and less easily scattered, while blue and violet light waves are shorter and more easily scattered. However, our eyes are more sensitive to blue light and less sensitive to violet light. Moreover, there's another player in the game: our sun. It emits light that's stronger in the green to yellow part of the spectrum and less strong in the blue and violet part. Hence, when you combine all these factors, it's the blue light that gets scattered across the sky most prominently. Now, what happens when this colorful sunlight meets the Earth's atmosphere? Let's find out. When sunlight, with its array of colors, enters our atmosphere, it encounters countless tiny particles. These particles, known as atmospheric particles, are a diverse mixture of elements. They may be gas molecules, dust, or even tiny water droplets. Each of these particles interacts with the sunlight in its unique way, but let's focus on the most common interaction: scattering. Scattering is like a microscopic game of tag between light and particles. When sunlight, composed of various colors each with a different wavelength, tags an atmospheric particle, it gets scattered in different directions. But here's the fascinating part: not all colors play this game at the same pace. Blue light, having a shorter wavelength, gets scattered more easily and in more directions than the other colors. It's like the excited kid in the game who runs around tagging everyone. This higher rate of scattering is due to a phenomenon called Rayleigh scattering, named after the British scientist Lord Rayleigh, who first studied it in detail. So, as sunlight pours into our atmosphere, the blue light is scattered all around, bouncing off particles and filling the sky. When we look up, we see this scattered blue light coming from all directions, giving us the impression of a blue sky. This scattering of blue light is what paints our sky blue. But what about those stunning sunsets? Let's see how they fit into the picture. Ever noticed how the sky can turn from blue to a dazzling display of red, orange, and purple during sunrise or sunset? This transformation is not just a beautiful spectacle, but also a fascinating scientific phenomenon. As the sun rises or sets, its light has to travel through a larger portion of our atmosphere compared to when it's directly overhead. This increased journey means that sunlight interacts with more atmospheric particles along its path. Now remember how blue light, with its shorter wavelength, gets scattered easily? Well, during these times of the day, even the longer wavelength red, orange, and yellow light gets scattered, painting the sky with their hues. These breathtaking displays of color are not just limited to red, orange, and yellow. Depending on atmospheric conditions, you might even catch glimpses of pink, purple, or gold. So the next time you watch a sunrise or sunset, remember, you're witnessing a grand light show orchestrated by nature itself. So, there you have it. The sky's blue color is a result of sunlight interacting with our atmosphere. To recap, sunlight, though appearing white to our eyes, is a composite of many colors, each with its unique wavelength. When this sunlight enters our atmosphere, it meets numerous tiny particles, including gas molecules and dust. These particles scatter the light, but not all colors are scattered equally. Blue, with its shorter wavelength, gets scattered far more than the rest, painting our sky with its distinct hue. But the magic doesn't stop there. During sunrise and sunset, the sunlight has to traverse a thicker layer of the atmosphere. This increased distance causes a greater scattering of other colors, resulting in those breathtaking shades of red, orange, and purple we all adore. Thank you for joining this enlightening journey. Remember to like, subscribe, and comment. We'll see you in the next video.